I try to time it with the music. What's up? Is it just me, or is the camera kind of low qual? Like the resolution's down a little bit or something? Oh well. Oh, yep. I know it was true. Hold on. Why does it do that? I'm trying to think if I can reset this thing without having to like close and open OBS. Let's see. Let's do this. No, wait. Okay, that's good. Let's move it over here. We'll flip it. And I think I can do... Yeah, okay. That's good. Okay, good enough. Okay, so what's on today's agenda? Yeah, sweet. So, what we did last stream on Thursday was make this this effect, this fisheye effect. Let me show you in the code. This thingy here, which, let's go to that component. Yeah, so this is a fisheye effect that is all done kind of in the like JavaScript side. But I wanted to, you can also achieve the same effect. So this fisheye effect is that around the corner, or like around the edges here, you get this curvature. Which you wouldn't get if you just rendered normally with like a normal perspective camera or orthographic camera. So it creates like this lens distortion effect that makes it look like it's like inside of a sphere or something. Went into a little bit of detail on that last stream, so I won't recap it, or I won't like rehash it here. But you can also achieve this effect with a post-processing pipeline thingy. So that's what we're gonna do today, and it'll be pretty cool because we're gonna use three.js, but we're also gonna use like this new, well, newish three.js shading language that they've been working on. And I'll drop that in the chat. So this is something that helps you create shaders. So currently, if you're using like a WebGL renderer in three.js, you have to do this. Like if you want to make custom shaders or branch off of shaders that are already in the library, it's really tedious. And you have to do this like replacement strategy where you actually replace fragments of the shader code, like this actual source like string. So the way that it works is you have your shader in a file that's just like a string, right? It's just like a text file. And then you load that at runtime, and then you compile it at runtime. But there's no good way to kind of modify that shader. You have to go in there and actually replace parts of the string. at runtime. But TSL is a little different in that you have these like this whole library of helper functions that you compose to make shaders, and it's kind of like a, I don't know too much about it, but it's more like modular for sure, and everything is kind of like a node, and then you just kind of branch off these nodes, and you can like tap into certain parts of the subtree and stuff. Um, you know, and then like you can save all these things to variables and stuff too, so they're really easy to get like a reference to something and then use it or reuse it in different parts of the shader and so on. You'll see what I'm talking about when we get there. But luckily for us, somebody's already done the math that's involved in doing all this. So we're going to copy this. This is an article by somebody here, which demonstrates how to do that lens distortion. And this is the actual shader code, so this is the GLSL, but we're going to convert this to TSL, which will transpile to Wigzil because we're running in a web GPU renderer. But it would also transpile to WebGL if for some reason like this was a WebGL renderer. So that's another benefit of using TSL, is it you can run, or you can like convert it from TSL to Wigzil, or you can convert it to WSL, or sorry, you can convert it to GLSL. There's so many acronyms. So that's kind of what we're going to do today. We're going to make TSL shader. We're going to convert this to TSL and then load it up. And the way that we're going to do this is kind of like, well, exactly kind of like using a render target, but TSL does it a little bit more abstracty. So we don't have to create like a render target. We don't have to do any of that. There's already mechanisms. Who's this? Okay. New streamer art? I don't think so. But you can share it, I guess? I don't know. Well, your account's only been created for a day. I don't know if I trust you. How do I... Well, I'll just leave it like that for now. Okay, anyway, yeah, there's already mechanisms in place to get like a render target. And then you can just use that target as input to a texture helper. And the idea behind this distortion effect is that you're just modifying UVs. So, because the UVs are just used for texture indexing here, we create UVs that are going to sample the texture so that it looks like that distortion effect. Because normally you would sample the texture from like 0 to 1 on the x-axis and then 0 to 1 on the y-axis. But the UVs are going to be modified so that they're sampling the texture so that it looks like that fisheye effect. But we're going to need to set up a lot of code first before we get there. So let's bring in that. Let's see. Gotta go back here. So let's do the normal thing that we do. Set up the boilerplate. So now always just get this from some other file that we got. Okay, don't have this yet, so let's bring this in. It's good. I'm not gonna do this. Not gonna do this. We will do that, but we will do some normal camera that we're gonna get. This resize function is from us. Render size we don't need. Here we actually do need to modify the camera that we're going to use, but we'll do that in a moment. Here we'll put a scene down, and let's create those. So that's a new scene. So you always need these things when you render. You need something that you're going to render, and you need a camera for rendering. So those are imports from WebGPU. Just a moment. Yeah, so we got those. This camera thing, it needs to be updated when the renderer size updates. So let's say set aspect ratio. And the aspect ratio is the canvas width divided by the canvas height. Yeah, so now we're rendering. Let's actually put something in the scene. Let's just put a box. That's new box geometry. We'll move the camera along an axis so we can see the actual geometry or the mesh. So I'll probably import. Oh wait, now we do scene, and then let's add that mesh to the scene. And then this is probably not imported. Yep. Okay, where's our box? You know, this should work, right? What am I missing? Something silly. Oh, I gotta look at. So, let's make the orbit controls here and now, so we don't have to do them later. So we'll call that orbit. And then for some reason, like, it doesn't get the import right. Well, that is a valid import, but I'd like to import it from here instead. And you pass in the camera, and then here we have our little helper attachment for attaching the event listeners. So it's called controls, and you attach orbit. Okay, there he is. So to like easily see the distortion effect, let's put the camera so that it's not like up here. So right now it's been translated along this axis. And you can imagine that that's 1 unit right, 1 unit up, and then 1 unit back. And then it's looking at the center. But let's just translate it along the Z. So that's super easy to do. I'll just use the, you know, the Z. We'll do a unit vector in the positive Z direction. So we're kind of far back. Let's put the camera a little closer. And now when we apply this effect, we should see, you know, these edges will get rounded, but that'll be a little bit later. So the post-processing is at a high level. You've already rendered the scene to like the canvas, but instead of rendering to the canvas, you want to capture that in a texture, and you're going to modify that texture any way you want. Like you could apply a grayscale to it. You could do like color correction. There's all these different effects. If you look at the shader document or this TSL document, they have a whole post-processing section here, and you can do all these different effects. Unfortunately, there's not a lens distortion one, but that's what we're going to create today. So in order to do this, we're going to steal some of these little like sample code that they've got. But I want to start with, yeah, this render pipeline. Where does that get made? Right here. So render pipeline we're going to make in the attachment. And I'm going to like gloss over some of the, I'm not going to really explain what the render pipeline is. You can kind of go in the docs and see, like they talk about it here. What does it do and what it's used for and so on. But we're going to need one if we're going to do any kind of post-processing. If we're going to modify the texture that gets generated or written to when we render the scene, we're going to capture that. We're going to do things with it. So the step one is just to create this render pipeline. Got that here, and then you pass in the renderer. And then you can create a scene pass, it looks like, but we don't need that to be in the attachment. There's a pass, give it the scene, the camera. And now each of these, not each of them, but a lot of these TSL nodes have these kind of different nodes that you can tap into. So you can actually set them. So we're going to set the output node, what is actually output in the shader, or like what's the final output. We're going to set that to the scene pass, and we'll probably give this a different name later on. And then rather than rendering with this guy, we're going to call render pipeline.render. Okay. So yeah, here you can see that you can get texture nodes for different, this is called multiple render textures or targets, I think. I'm going to skip over all that. But now you can take the texture node here and you can do things with it. Like here they're applying a blur and they're grayscaling it. So let's try that out. So we take the scene pass, get the texture node, I save that in a variable, let's do that too. So that should be the actual like texture, and then if we just call texture with it, down here, where is it? You can actually just call this like texture. The value, we're going to put in the output, and then we're going to bring in this helper function, this UV thing. So if we write this, we shouldn't see any difference, and we don't, because we're just grabbing that texture before we do, like we're not doing anything special with it yet. Like normally it would just, you know, do the normal UV stuff, but we're kind of like pulling that part out of it so that we can do things with it. But you can imagine, like, if I just pass grayscale here. Now I can grayscale the texture. And I don't think we'll see anything different. But let's do a blur. Box blur, what's it? Let's see. Gaussian blur, let's do a Gaussian blur. I don't know if that'll... Yeah, you can see there's a blur now here. So now we can like modify the output node. And this can be like any node, I guess, as long as it, you know... Well, the types in here are a little strange, but... I don't want to go into detail about that either because, like, the TSL stuff is, I don't know, it's very young, and it's easy to work with, but the documentation just isn't as complete, I would say, and that's probably because it's still like experimental, give or take. Um, so you kind of like as you work with it, you kind of learn like what different things you can do, what's acceptable, and that sort of thing. But here's what we'll do. So the whole objective is to change what gets passed in here in this UV, the second argument to texture, is what we need to modify. We need to modify these UVs. So that's where we'll actually go to the code here. And you can see down on the bottom here, they have this UV. So this is the fragment shader. This is going to be called for every fragment. It takes a varying here, so that gets created in the vertex shader. And that gets passed along to the fragment shader, do some more math, and it's using that UV as a sample, like sample index into this texture, this T diffuse, which is declared here. So the first thing we need to do is this part here. There's a two-step process. We do the fragment. Well, this is how it is in graphics programming. But you run your vertex shader code. It may pass some information down into the fragment shader. So normally you would do like your vertex shader does this logic here, this math here, which does a lot of projection math and calculates where to put objects in the scene. You might do scaling and stuff, you might do rotation and stuff like this. But anything that doesn't need to be calculated per fragment, you can also do in the vertex shader. And that way you're not, let's say you had a cube and it's got, what is it, 8 vertices? You're only running that code 8 times rather than running it, however many times that fragment shader is running. The fragment shader is going to run for every fragment within that like mesh. So you got 6 faces, and then this guy, it's going to run for all of these fragments, even though we only really need to run it once. And there's a trick to do that. In TSL, there's this render stage, or it's a vertex stage. Here, computes the node in the vertex stage. So it's going to return a node, but it only runs in the vertex stage. And then when it, vertex shade, and then the return from it will be available in the fragment stage. So all these things that get declared here, we can just do them in the vertex stage, and then access them in the fragment shader. So this is kind of be like a one-to-one conversion. You might actually be able to do all this just in the JavaScript, but I'm gonna do it just to be sure that we're doing it properly. It's not going to be very optimized at first, but I think just to convert it, and then we'll worry about what like optimization techniques, or we can go through and refactor it as needed. And I actually downloaded this file where at the end of this, I don't know if it's down here, this source. This guy actually did a three.js example, and you can download the source for that example. Is this the one? Yeah, so I have this locally, so we can actually take a look at the source code. And I'm going to bring that up down here. And I think actually this fragment shader code and GLSL code here is inside of that folder, this link here. So I'm gonna close this for now. And we'll bring that up side by side with this. Remember my key maps. So I think it's in downloads. This one, and then this file here. So this is some old code. You know, it uses like var and stuff. Don't know what version of three.js it uses. But apparently this was written more than 10 years ago. So yeah, things are that old and they still run and they still work, and that's good. But a lot of this is pulled from that article. So there's a lot of like math involved too that I wasn't so sure on. Not like sure on, but I didn't want to actually derive it and stuff. I just want to use it in this case. Usually I like to go into those things and actually learn how they work and, you know, all the... What's the word? Like, you learn how it all comes together, you know it in detail. Or you can just use it. You say, if somebody else did the hard work, I'm just going to use it and apply it. So that's going to be what we're going to do today. I'm not really going to go into it. Maybe one day I'll check it out. But this guy has, in that article, he has like a notebook. I don't know if it's a Python notebook or something, in which he derives all the equations and stuff and the formula. And the reason this looks so dark is because I changed the background so that it would look like I didn't want to look at this and read this and all that on stream, so I just made it so that it's not so blinding when we look at it. Because if you were to reload this, the background is actually supposed to be white and so on. But anyway, so down here, let's cut this out for now. This height depends on the camera aspect. Oops. So let's do all that here. This camera aspect gets recalculated. You can see here that it gets calculated based on the width and height of the canvas. So let's actually save that in a variable. What is it? Client width. Like so. The height here, they've got a couple of parameters up top. So, you know, it's referencing this horizontal FOV and this camera aspect. So let's save the horizontal FOV up here like they do. And the strength. These may need to become uniforms, but we'll just call them constants for now. Okay, we got this. So the height here is equal to Math.atan. This actually comes from MathUtils now. And it's degree to radians. Horizontal. So Math.atan expects the argument to be in radians. So this makes sense. And we're going to cut that in half, whatever it ends up being, and we're going to divide by the aspect. So if you're kind of familiar with like cameras, this is kind of like the field of view or whatever is like this. You're taking half of that field of view. Let me draw it. Oh, whoops. So your camera is like positioned here. Here's your near plane and your far plane. Your field of view is this angle here, this theta. Well, let's say that this is theta. So it's taking half of theta, which is going to be this here, this angle here. Maybe we'll call that, is this phi? I guess that's just phi. So that's what this is doing, is divided by 2. And then dividing it by the aspect is kind of like adjusting for whatever the camera aspect is. And that's the height of the... how are they using height? I think height's going to be used in the vertex shader. Yeah, right here it's a uniform. So maybe now that we see this, we can convert these to uniforms. So that's going to come from horizontal FOV is not a uniform, but this one is. So uniform comes from TSL. Okay, that height we've got. And the camera field of view is based on the height. So we'll do const FOV is 8tan of height times 2. I like to put these in the beginning. And I never really divide by 2, or I always try to do multiplied by 0.5. And the reason is because in my mind this is a scaling, and scalings are always multiplications. So division is really just a multiplication by, 1 over whatever you're dividing by. And then this 180 over math.pi here is actually pre-calculated in Math.utils, or MathUtils. What is it? So atan takes... No, the FOV is in degrees, so we need to go from radians to degrees. And what do? We set the camera FOV to be that. And then the last thing we need to remember to do is set the aspect. And then we actually need to update the camera projection matrix. Okay. So that height looks like it's also a uniform. So let's make a uniform for that guy. Let's just set it to 0. Not sure what we set it to in the beginning, but it'll be calculated down here. But now that it's a uniform, you have to say .value. So this holds, the value of the uniform. And then here, access it like that. And they're saving the aspect ratio as well in a uniform. Aspect ratio, probably want to call it, set it to 1 because usually you divide by the aspect ratio. Like here. And here we can do aspect dot, or this is aspect ratio dot value. Access that here as well. And here. Okay, now we got everything set up. So this is going to run anytime we resize the renderer. We also need to set camera properties. But we're going to use those properties as uniforms into the shaders as well. So that's kind of converting this. Not this, but this part of the code has been converted here. And we got the uniforms up top here that we can work with. So the next step is to create all these, or actually convert this code now. So I think I'm gonna pull up that document now because it's easier to read. It's better, like these are all just strings. Let's do that. Okay, so this position thing we're not going to worry about. That's already calculated for us. We need scaled height. And then we do strength. So we can't do times here because this is actually a uniform node, but it has a method on it for multiplying. And we multiply it by the height. So that's conversion of this. And that's kind of what we're going to do. It's just going to walk through this code here. And you can do that because you can just save these things into variables. Which is another really nice part about TSL is you can kind of treat it like you can do all your shader code, it seems, or it feels like, or that's like the look and feel of it is you're just kind of writing JavaScript code again. So we call cylindrical aspect ratio. That's going to be the aspect ratio, which we have in a uniform, multiplied by the cylindrical ratio. Okay, we have the aspect diagonal squared. Mul dot add. So we have an add here. Okay, diag squared, scaled height, dot mul scaled height, dot mul aspect diag square. And then we have this signed UV, so that's UV. So we're going to do this kind of flipped because we have to do like this method chaining thing. Mul. So this is taking this UV. I know what this one's doing. This one's taking the UV that ranges from 0 to 1 and shifting it so that it ranges from -1 to +1. So if you take 0 to 1, you multiply by 2 on both sides to get 0 to 2. And then if you subtract 1, you're going to get -1 to 1. So that's kind of what this is doing. And then you're going to add that, or let's see, signed UV gets used here. So it's scaling some value, and then that value gets passed through here. The dot product should always give you, like if you dot anything with itself, it should give you a positive value. Yeah, it's just, so it's kind of tricky to know like what each of these are doing, but that's kind of the fun of it, is you don't really have to know. So I don't like saying that or doing it that way, but it's kind of a short notice stream, so that's kind of what I'm gonna go with today. So where are we? Got the signed UV. UV multiplied by 2, and then we're gonna add a vector. Or actually, I think we can just add -1, and it should add it to both components of the vector. Okay, z is square root, which is another ESL node. Diag squared. I'll add 1. That's going to be multiplied by 0.5 and then added to 0.5. And we have this ny that is z.sub 1 dot divide cylindrical aspect ratio dot mole Okay, I think that's right. And we have, this is the vertex. So these things that are varying here are what we need to declare as vertex stage. So that is VUV dot. Takes in a node. It's this here, so square root ny dot mole vector 2. But I think we can again just multiply it by cylindrical. Oh no, this needs to be vector 2 because this is. So these were the same value here. These are different values. So we actually need to pass in a vector 2. This we'll get from TSL. And 1. And then after the square root. Oh no, we're actually, yeah, after square root, multiply by this vector 2 guy. And then we're going to multiply by signed UV. I want to make this capital. Okay, is that right? I think so. And then VUV is also vertex, or it's varying passed down to the fragment shader. So let's calculate that. Vec3 dot mol z dot add and what's up here? Oh, vec3. Do I need to bring that in? Yeah. And then I do this plus equals UV here. So I'm going to give this a different name. So this is a vec3. But we need to modify the XY of the VUV. So let's do VUV. I'll just put a thingy here. How did I do this? Look at my notes. Oh, okay. I don't know if this returns, yeah, I'm gonna leave it like this. But this thing here, I'm gonna jump down to this, and we're gonna do this step here. But that'll make it run in the fragment shader. So this should return, still return a, yeah, vec3. Okay, that's what I want. Oh, I need to make this vertex stage. 'Cause Actually, all of these need to be vertex stage, right? I think so. But I don't know, if you don't use scaled height in the fragment shader, I don't know if it gets passed along to the fragment shader. But I think that all of these have to be vertex stage. So let's see if I can do this quickly. Yeah, so we'll do... No, wait. Okay, I remember how to do this. We do QQ. And then Q. So now I should be able to do at Q. Yeah, there we go. At Q. Alright, sweet. So this set XY, we're going to do it like this. Vertex stage, we're going to... Can I copy this? Is there a copy function? So why don't I get autocomplete? Okay, there we go. Get all the methods on this thing. Holy moly. Flip things too, that's cool. Can I clone it? No. This is tricky. Okay, who knew that this one would be so tricky? Can I do add XY? You know, what I can do is this. Yeah, okay. And then we're adding 0 here. Yeah, I think that should be fine. Because the UV is just a two-dimensional thing. But if we want to add to the XY here, what do we add to Z? Well, we just add 0, and then it's the identity. Yeah. So now our new UV, that's going to be dot. Where's dot? Multiply vector 3. Dot add VUV. And then that texture thing. So this 2D projection thing, this is actually different than texture 2D. And what it does is this UV, you can see here that it's not a two-dimensional vector, it's a three-dimensional vector. And it will take the X and Y and do a normal texture sampling, but then it divides that by the Z component here. There's no equivalent of that from what I read. There's no equivalent of that in Wigzil. So to compensate for that, you can do it yourself. So you would do here, you would do you do that X and Y, you divide out the Z, yeah. We can actually jump down here and do it. We'll do uv.xy.div. So this will give us a 2D vector, but this needs to be like that. So this is, yeah, a node of vec2, and then we're going to divide out .z. Yeah, we don't need this, and this, and this. I don't know if it worked. Let's see. Okay, looks like it did work. So this strength thing is how much it's been applied, but a very subtle, like, curvature here. So if I turn the strength to 0, yeah, let's actually make it 1 so that it's like really pronounced. And then if I make it 0, you get no like curvature. We go like really high, you get a lot of curvature. And because this is a uniform, we can actually create controls for this thing. So let's do that. We'll make a little container. Give this a class of absolute. Bring in our pane container helper thingy. We'll say it's top right. And then we need to attach a pane. What does this take? I forget. Yeah, the config, so title, we'll give it controls. Top 2, right 2, why is it on that side? Top 2, right, oh, this needs to be relative. Sometimes I get these things backwards. I'm gonna restart because it looks like something is causing it to run a little slowly. Okay, so we see it over here. Let's put the controls in there. The second argument to this is the init function for the pane. So pane.add binding. I wonder if we can just pass in strength here. And then here you can set like the min and the max. So the min we'll say is 0, max is 2. We'll say the step size is 0.1. So we're at 2, and then if we control this, you can see it causes it to bend and stuff. And let me look at the inspector just to be sure there's no warnings. Yeah, everything looks good. We could do the same thing with these other uniforms. Not the height, but let's look at that example again and see what they've got that you can control. Here. So the FOV, the strength, and the cylindrical radius, or ratio. Horizontal FOV. Looks like they allow you to go all the way down to 0. Or 5, okay. We'll go down to 5. Max maybe is 160, I think. Yeah, 160. Here we'll do steps of 1. Now let's see how that affects things. Oh, it's horizontal value. Oh yeah, it's not uniform. How does this get used? Why does they have it? Oh, he doesn't have it as a uniform, but when this thing updates. So instead of this, we need to do that. Oh, capitalize. On change. Well, if this is an object, so where do we use it? We use it here, right here. But it's being picked up whenever this renderer updates. So I don't know if I want to mess around with this one. It's easy when it's a uniform because it'll just be picked up in the next render. But it's not really being used in the shaders. And this is not a callback. Well, it is kind of a callback, but it's not like event-based. So when something is too difficult or I don't feel like doing it, I just don't do it. Okay, let's do add binding. What was that other one? Strength, and then we had cylindrical ratio. And the height. I don't think you can adjust the height though. Yeah, just the cylindrical ratio. Okay, what are the min and max here? Let's go all the way down to 0 and up to 4. Let's see what that does. Well, maybe 0.3 to be safe, because there might be a division by 0. Oh, we need to give these different labels. This label here is the cylindrical ratio. Can I make this 0? I guess. Where is it used? Here. We're just multiplying it there. The only place we do a division, I think, is down here. Where was it? Here, so if this value ever is 0, then we have a problem. So it's only ever 0 if this is -1. How is it? How can two numbers ever multiply to be -1? They can't, so I think we're safe. In that case, I kind of want to make this value of 1. What is up with this stupid... When I save it, it shouldn't be prompting me with this. I gotta check that out. Okay. Let's see. Doesn't I think this has to do with Vite. Or yeah, Astro and some runtime stuff, so I'm not worried about that. Let's actually load in that model and compare it with the other one. Let's split this. We'll bring in that. It's the same kind of loader stuff. Probably want this in a module script tag. That's annoying, that stupid... I don't know what causes that. Okay, let's pull that back up. What was it? So this is imported. Okay, we have this little bit of code we need. Not gonna bother with this mesh anymore. We'll add it to the scene once it's done loading, but we need this URL. Oops. Oops. Why does it do that? Where is this defined? So that can actually go up here. Well, no, I like to keep the imports. You know, in Svelte you have module scripts. I want to keep the imports in the non-module script. That way they're all together. Okay, it looks like it loaded, but it's upside down. Something's wrong here. Are we getting the curvature thing? I don't think so. Why is this all flipped up? Flipped up and all around and stuff. Look at the notes again. Oh, I know why. This needs to be like this. We're still upside down. What's the problem there? Probably some sign got flipped somewhere. Wow, 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 wow. Oh, before I forget. I don't know. I don't know why we're upside down. I mean, there is easy ways to fix this, but I'd like to fix it in the shader code if I can. Because if we do, let me just do a sanity check. So if we just set this to UV, it should be upright, right? Too many warnings. What's the warnings? Oh, we're not upright. Or wait a second. Wait a second. Why is this thing flipped? Do I need to flip it somewhere? I mean, you could do like here we added the UV. Or wait, let me pull that back. Divide by this, but we can do this y needs to be 1 minus y. So if we add vector 2, 0. Oh, here we do this. We do vector 2. So I want this to be equal to x. This is strange. How do you do 1 minus the y on just one little... Can I multiply it by -1? Is that the trick? Maybe this is what I'm supposed to do. Oh, I didn't like that. At least one argument. I got an argument right here, fool. Oh. We don't add anything. That's not right. If I multiply by 1, should be good, right? That's right. So why doesn't multiplying by -1 do it? Yeah, these UVs... It needs to be 1 minus that, I believe. Because what you kind of want is... You got your UVs, let's say they go from 0 to 1. But you want to flip that and go from 1 to 0. So an easy way to do that is to take 1 minus this thing. But then your x's will be out of order. Well, let's just try it. I think we have a 1 minus. Now our position is all wrong. We were flipped and the... I don't know if you guys remember from last stream, the arcade machine was on the wrong side. So that, I mean, the fact that the U, like if I pass in, let me put this back to normal. The fact that doing this makes it upside down tells me that the texture itself doesn't have its flip Y set. So can I modify output? Where's output? Flip Y. What does this take? Do I just call it? Is it in the docs anywhere? No. What the heck? Does this take any arguments? I might have to save it like that. Oh, is the song over? That was it. It's already been, yeah, it's already been an hour. Okay. This is a good soundtrack. Well, I don't know what to listen to now. See, I don't remember this. YouTube automatically start playing music if you're on that tab. Or play the video if you're on that tab. I got no music recommendations. I watch too much YouTube. Let's just put on something generic, I guess. This'll work. This is fine. Oh, what the heck? My Bluetooth. One second here. I don't know if that's too loud. Oh, you guys can't hear it. There we go. Okay, back to normal. And we're checking if this does the trick. Maybe a little too loud. Oh, it doesn't like this? Is that my whole problem? Is that why it's doing all that? No. let's do const texture. Let's do t because texture's already taken. Output dot set y to be 1 minus of. Where's 1 minus? This is crazy. Return 1 minus the parameter. Yeah, I should be able to pull this in from TSL, right? Okay, there it is. Let's do 1 minus output dot y. And then down here, we'll just use t. Oh, what's the problem now? You don't like this? It's not assignable. Okay, even though it's not assignable, did you still work with it? No. This is annoying. Set y should return. See, it returns a vec. Okay. Oh, texture. Oh no, this is output. Okay, that's good. So the x uv.y 1 minus that. There we go. But I don't like this. This feels weird. I don't know. So this is without any the UVs that we were working with. This UV here, this is just based on the normal UVs. So if we take that, we'll just pass in. Yeah, this is 2. So uv.x 1 minus the thing that we created, that y. And then we divide out. There we go. But, you know, the way that it's like centered is so wrong, isn't it? What's the problem here? Yeah, it's like only affecting the top or something. Ooh, look at that. That's not right. Maybe I need to do 1 minus over here. So I'm just gonna play around with it at the moment. We'll do that, and then we'll pass in a vec2 down here, where we'll do that. So we've already divided out or scaled it by the z value. So this is uv.x, and this is our uv. So what was it? uv underscore. And we'll do 1 minus. Okay, I think this is so strange. Like now it's pushed over here. It's not centered. Let me put that mesh back in. It'll be easier to see, I think, if we put something that's simpler. Let me put this back to UV. And then when we do the scene, right here we'll do this. Oh, is it because of where the camera is? I don't know. 0, 1, 1, 1. Okay, this is 0. Yeah, so we've got no strength. That's because we're not using the UVs that we made. UV underscore. Okay, this is definitely moving it downward. Oh, I'm not crazy. Or am I? Aha, this is not right. Okay, where is it? There we go. That's better. Now we do this. Oh, we do this. And then what did we do to flip it? We did vec2. So it's underscored. UV underscore dot x. 1 minus. What is this song? No track list? Oh, come on. Oh, this is Majora's Math. Okay. Come on. So it's like the center of the scene is like not in the middle or something. I wonder if we calculated a bounding box for this thing, if it would be in the middle. It looks like the center. Well, the 0, 0 is right here, but the center is like up here somewhere. So I wonder if when we get the GLTF scene, if it already calculates its bounding box. Let's just log it out. It's on the geometry, I think. But this is a group, so it doesn't have any geometry. Objects in that group have geometry. Alright, so let's do this then. Box that set from object. What is this? GLTF.scene. Center wants a vec3. So this is the center of the scene. That's what we need to set the orbit target to. So where do we create the camera? Right here. We just say orbit target. Oh, we can actually just save it into the target. No way, we don't need that. And then the camera, we've got to make up here. And I think when you set the target, you also have to update the camera. I think. So now it's looking at the target. Or it's orbiting around that target, which is the center of the scene. But maybe now we change these values. Or not. I don't know. Is this negative? No, it needs to be positive. Oh, I think because it's... Yeah, but what if we pull it back even more? Okay, there we go. That's better. Wow, 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 wow. Let's clean up some stuff. That flipping of the Y, though, that's strange to me. I have to look into that. Does this take any other parameters? Level node, bias node. Don't know what those are. Maybe it's like the level has to do with the MIP maps. MIP maps. The bias. Node, I have no idea. Texture. Oh, that's cool. They have a cube texture. Yeah, there's so much stuff in here to play around with. I was surprised that they don't send the aspect ratio in here. But I wonder if that's available. Screen right here. So I guess you could calculate the aspect ratio. Screen size returns the frame buffer size in physical pixel units. So maybe we don't have to send in the aspect ratio. Right here, we can just do this needs to be div. Screen size, we need to bring in. Y. Okay, that's cool. We eliminated that. So down here, well, I guess we don't know if we really did eliminate it, but let's see. Yeah, that's a little cleaner. In that case, well, this is fine. So here we update the camera, we update projection matrix. What else do we have? The height, so everything is kind of based on the height. This is the problem when you use the code and you want to know like what all these parameters do, but I didn't read through the math involved. So it's kind of like I don't know what I can modify. But I don't like the fact that like this height and this aspect ratio are kind of like well, the height seems like something that, yeah, I don't know. It feels like there's some kind of like disconnect between these things. Because normally you would just set the FOV, and I'd like to calculate the height from the FOV. But it looks like the FOV is calculated from the height. So you could probably try to, you know, say here, set the FOV. Right now it's a constant 140. But like imagine, you know, a control in here that says set the FOV. And then you calculate the height based on that. I believe it should just be a matter of rearranging this. Maybe I'll explore that a little bit. So the height is, or let's see, let's use the FOV. So F for FOV is 2 times atan of the height, and then times this constant. So to isolate h, let's move the constants to the other side. That's F over 2 times C atan of h. So how do you get rid of this atan? I don't remember. So let's use Wolfram alpha to do that. We'll say solve for h. What was our equation? FOV, well, let's call it F. Holy moly, what if it's a real? Assuming that things are real. Oh, it's just tan. C is... Okay, so these are the same. So it looks like the height is equal to Math.atan of the field of view times 2 times that constant. I think. And these are real numbers, so we don't have to imagine. These accommodate for imaginaries and stuff. So let's see. We got the FOV. That's the horizontal FOV. We can just take camera.fov. Let's do Math.atan. The FOV is in, oh, it's right here. Is this the, divided by 2 times Math.Utils.read R2G. Oh. I don't know if this will work. It flipped it upside down again. Why did it do that? Let's do... When we make this camera up here, field of view, let's put in 140. Ooh, look at that. That doesn't look right. So I guess, I don't know, I'd have to look at the numbers and see, or look at the math and turn it into like equations and see what we can get away with. And like, all this might be explained in that article. This is this right here. So what happens if I just set it like this? We don't do this. Yeah, that's correct. That I feel better about. So many people outside walking and riding bikes. Probably go for a walk later. See this FOV thing, now we're like so far away. But the camera FOV, what was that being set to? Oh, it's being set based on the height. So the way that it looks like it works is, what do you want the FOV to be? 140. You know, calculate the height for that. Now, to compensate for the stretching and all this, now we set the camera FOV based on the height. So all this can be substituted in here. And that height is something that we need to use in the shaders as well. Yeah, I don't know. It's gonna bother me that these things are like this, but what was I? I'll put it back to normal. But I don't know if it'll bother me so much that I won't be able to sleep. I'm just gonna probably try to move on to the next thing. Yeah, so that's that. I'm trying to think if we can put these things side by side. Oops. Okay, am I crazy or did it flip it? Had it flipped for some reason. Okay, in that playground Astro file, let's bring in the other app. This is post-processing. How do you spell that? Processing. And then the app here, we'll pull from basic. Post-processing. Maybe I should put these on separate pages. Because what this will do is put them side by side, or top and bottom. But can I put this in a div? And then give this flex, what is it? Flex column? Flex call or something? Oh no, I want it to be flex, well, I guess flex row is the default. Dang it. Go back. What happened? So this one has a much higher field of view than this one does. If we go back to that example, I think 90 is the default for field of view. What the heck? Oh, I didn't expect that to happen. What's going on? See, this guy's field of view just works. You know, what's happening here is that field of view is going like way down like this. And you'd only expect to see that green cube in the middle because you don't have so much like field of view to work with to see everything else. I mean, maybe it would be nice to add controls for this field of view thingy. But you know what? I don't know. Let me put this back to this thing here. But I was really, I mean, I'm really surprised that putting that field of view to a value of 90 causes it to disappear. I don't think that's correct. So, I don't know. I think I'll have to figure it out off stream. Because should still see something, even in this case. What if I do like 110? Oops, 110, 100. Yeah, it's just getting smaller. That's the opposite of what I think should happen. It should get bigger as you get closer and closer. Whereas the field of view goes up, like you see less and less of it. Because these objects have to share the screen space with so much more stuff. So I think there is a bug somewhere, but I'll have to track it down. I don't know. But I think it's working otherwise. Definitely can see that curvature. I think I'll fix that problem. I'm trying to think what I want to do next. Kind of want to do something. I don't know. It feels nice to use TSL. I feel like I need more practice with it. But I might take a look at some other examples of shaders and stuff. Maybe more post-processing shaders. There's a really good article. I don't know if it's find it or not. Yeah, I actually did. This is like a survey almost of what you can do with post-processing shaders. So we might explore that next stream, and next stream will probably be on Thursday. Thursday? Yeah, Thursday. Sunday, Monday, Tuesday. Yeah, Thursday. So I might take a look at some of these and implementing them in TSL. Things like this. I had an example on the website like that, but the TSL got updated and I couldn't figure out like there was breaking changes and I couldn't figure out what it was wanting me to update. So I just threw it away because it was kind of like a half-baked example anyway. But I think it'll be nice to go back and I think it was one that implemented one of these. It was like a dithering effect. Well, this is cool. Yeah, you can see like you can do some really cool post-processing effects. Dang it, what is the button to... There's some way to do this, but every time I go to do it, I can never figure it out again. Oh, here we go. I guess you click on the name. I gotta remember that. Okay, anyway, I've been stalling for too long. Come back on Thursday, we'll probably do some more post-processing stuff. I'm gonna fix this code here. Once it's fixed, I'll push it up to the live website. It's CI is broken right now, so I gotta figure out what's wrong with that anyway. I don't think the CI is the problem. I think it's something where it can't build the project for some reason. So some bugs are gonna get fixed. I got 4 days to figure things out. That's plenty of time. So if anybody's still tuning in, thanks for watching. I will be back on Thursday. Have a good weekend. Have a good Mother's Day. And see you guys later.